Welcome to our next very important video on our 4-8 example problems. On this one, we're going to be doing an anion, a negative ion, the arsenide ion. We have to find As, arsenic, on our periodic table of elements first. So let's take a look and see if we can find that. Here's arsenic right here. It is number 33. So we need to know that it starts with 33 electrons. Why? Because it has 33 protons. The electrons and protons must equal each other. But if it's 3 minus, it means it has 3 more minuses than positives. So if it's 33 positives and it's 3 minus, it must have 36 electrons, which should not surprise us. Why would it not surprise us that arsenic would want to become the arsenide ion 3 minus? Because if it gains 3 electrons, 1, 2, 3, it would have the same number of electrons as krypton, which is chemically stable. And we're going to get a look to see what it is that makes krypton chemically stable right here as we do arsenic. What does arsenic gain by getting 3 electrons? We will soon see. If we look on our periodic table of ions, we look right here. We also see that arsenic loves to become 3 minus and become just like krypton's configuration with electrons. Arsenic is in family Roman 5. Family Roman 5 wants 3 electrons to end up like Roman 8. So we're ready to begin. Arsenide ion. We know it has 33 protons. It's 3 minus, so it has 3 more negatives than positive, so we're putting in 36 electrons. Notice on this one, we have the As3 minus here. All the other ones, they put the symbol with the atomic number. When it's charged, they're just going to give us the charge and expect us to look up to see how many electrons it is. So let's begin firing in the electrons. First 2 are going to go into the 1s according to Aufbau. So there goes 1 into the 1s. And here goes our next one into the 1s. And now the 1s is full with 2. Which means, according to Aufbau, we can now move on and begin filling up the 2s. Here we go. We're going to start filling up the 2s with electrons. And it is now full. So now we can move to the next higher energy level, according to Aufbau. And we don't want to put them in going like this. Here, we're going to start filling this up. What rules am I breaking by doing this? Putting a couple down. And now I'm putting 1 up. Why can't I go down 1, up 1? That is breaking Hund's rule, which says single electrons will have the same spins until you begin pairing them up. So all the arrows go up in each of the orbitals, then we'll start putting the arrows down, showing an opposite spin. So all the arrows up first so that we're following Hund's rule. And now we can go arrows down. Following Hund's rule. Now I can move on to now that sub-level's filled up, I can move on to the next higher one. Now tell me what rule I am breaking right now by going from the 3s straight to the 3p before finishing the 3s. That would be breaking Aufbau's order of filling. We've got to fill this one before we proceed on to fill the next one. We don't want to break Aufbau, so I better put another electron in here. And now I can proceed on. Here we go. We now have 1 arrow up in each of the P's. We can now double up arrows down. We can now double up with the arrows down. As we are seeing right here. That one is full, and now we can move to the next level. The next level, after the 3p, the next sub-level energy level combination that we fill is the 4s. We have to completely fill the 4s before we go back down and fill the third level, D. So here we go. We're now going to go through and start filling the D. So the 3D is now full. I went ahead and put in the superscripts accounting electrons as well, just to see how many I have left. We have 2, 4, 10, 12, 18, 20, 30. Arsenic has 33. So let's go ahead and put in the 33 for arsenic. And then we will still need to make it 3 minus to give it a total of 36, because arsenide ion has 36. The arsenic atom has 33. So here we go. This is the arsenic atom right here before it gets its 3 minus. Take a look at this for a second. How many valence electrons does arsenic have? Now we haven't done arsenide. I haven't added the 3 extra. This has 33. Arsenide ion has 36. How many valence electrons does it have? Valence electrons are electrons in the outermost level. My biggest number here in front of any of the sublevels, my biggest number, if we look, is 4. My biggest number is 4. I have a 4 here and a 4 here. So my valence electrons for this thing are both in the 4s and in the 4p. I have 2 in the 4s, 3 in the 4p, for a total of 5 valence electrons. If we take a look at the periodic table of ions, here's arsenic. Well, it's the arsenide ion here, but arsenic would be in this square right here. We go up to the top, there's a Roman 5. There's a Roman 5 above that. How many valence electrons did we say this one has? 5. How many more electrons would it need to fill the 4p completely? It looks like we've got spots for 3 more electrons. What charge is the arsenide ion? The arsenide ion is 3 minus. I'm hoping that we're seeing now that the reason it wants to be 3 minus is it is able to be left with the outermost S, it's full. The outermost P is now full. Chemical stability comes, as we can see, it now has the same orbital notation as krypton would have, which is number 36. The noble gases have their S filled in the case of helium, and the noble gases will always have their outermost S and P full. So we're now beginning to see that one great thing about orbital notation is we can see that the arsenide ion is able to fill. When we fill the arsenide ion, we end up with that P being full. Now, very often when we do this, we'll want to put the additional electrons that were added in a different color. On your homework, when you're doing the ones that are minus, when you add electrons to it, I would like you to put those in a different color so you can see that those are the 3 that made it the 3 minus. Those are the 3 that the arsenic atom got acquired in order to fill the outermost S. Outermost P is now full, and it's achieved the octet rule. The octet rule, 2 in the S, and it now has 6 in the P. So we want our new number 6 put there. It has 6 in the P, 2 in the S, 2 and 6 is 8. We now understand where the octet rule comes from. The octet rule comes from having the outermost, that's the biggest number. In this case, it's 4, the first number. It's 4. We satisfied the octet rule. The next one we're asked to do is strontium ion Sr2+. How are we going to go about and do this? And we're going to do this a little faster. I'm not going to make you watch me click through all these. But first I have to find out how many electrons strontium has. If we look on the periodic table, we will see that strontium is right here. It has 38 protons, so it starts with 38 electrons. It is 2 plus. 2 plus means that it will have 2 more protons than electrons. So if it starts with 38 protons and 38 electrons, the electrons are the negative ones. If it starts with 38 of both of those, if it's 2 plus, it has to have 2 more protons than electrons. So I have to lower the number of negatives down to 36. So I've got to, on my final drawing, I should have 36 electrons. I'm going to go ahead and start firing them in there, and you'll return shortly after I have that completed. So during that brief intermission there, what I did is went ahead and filled in the arrows, and I did strontium atom. I did not do the strontium ion yet. We'll show you how and why it becomes 2 plus. Strontium atom has 38. We know the ion, we're going to have to pull 2 electrons away to leave it 36, so there's 2 more positives than negatives. Let's check and see how many we have on here. 2, 2, and 6 is 10, 12. That's 18, 20, 30, 36. Right through here, plus these 2 is 38. So now we have to make it 2 plus. I'm going to have to remove 2 electrons. Where should we remove the electrons from? The answer is always the outermost level goes first. So now I need to remove these 2. Those are the outermost electrons. If some other atom comes and rips electrons off, these are the ones that will go first. Here we go. Now, to show that these are being removed, I'm just going to make them like ghost things. I mean, I could just click and cut them out, but I would like to see when I'm done that there were actually electrons there that were removed. So here's how I'm going to do it. So there were 2 electrons there. They're not anymore. I made them ghost electrons. So I need to change this 2. There are no longer 2 in there. There's now 0 electrons left in there. Now, why would strontium want to lose these 2? Remember, chemical bonding, as we saw with the arsenide ion, was to end up with a filled S and P. Well, when strontium lost these 2 electrons, take a look what's happened here. This little, this sublevel, the 4s sublevel, and the 4p sublevels are left full. 2 in here, 6 in here, 2 and 6. Its new outer level, it's not really the valence, this is the valence, but the outer level it's left with is now full. So if we take a look at these things, this outermost, the original valence that had 2 in it, it lost those 2 when it became 2 plus. So now this 4s and this 4p are left full. This one has 2 in it, this one has 6 in it. 2 and 6 is 8. It satisfied the octet rule. It started with 38 electrons. It lost those 2. It now has 36. Like who? Well, if you're saying krypton, you are correct. Strontium started with 38. It lost 2. And now it has the same number as krypton. Krypton's chemically stable. We can see why. Krypton's chemical stability is because it has a filled S and filled P. The S holds 2, the P holds 6, 2 and 6 is 8. That's stability. We didn't address that strontium originally had 2 valence electrons here. So how many valence electrons did strontium originally have? It originally had 2. Now it has 0. It's lost those. What was the Roman numeral above strontium's column? Looking at the periodic table of ions, we see strontium's right here. It has 2 valence electrons. Lo and behold, the Roman numeral above it is 2. I hope you're seeing that these Roman numerals for these families, vertical columns, we call families, these Roman numerals are really telling you how many valence electrons they have. And we'll stop right here with these first 4 example problems. We have one more thing to talk about with, well, really 2 more things to talk about with orbital notations, and we'll pick those last 2 things up on our final video.